4.2, we're going to turn our attention to another type of function, and specifically this is called a logarithmic function. It is interrelated to our exponential functions. We'll talk about exactly how as we move our way through. And we will get started here at the beginning with the equation itself. So a logarithm, or a logarithmic function, has the equation f of x equals log. You'll see a little tiny a down beside the log. It is a subscript. The x that's next to it is on the same sort of, horizontal line, if you will, as the log. So you're seeing this happen where these are if you were writing on lined paper, they would be on the bottom line right beside each other. Every now and then I have students write things not quite the right perspective, so I want to draw your attention to that. You'll notice that little subscript a, we call it a base a, so this is read log base a of x, has the same conditions that our bases had when we were working with exponential functions. They can't be they can't be smaller than 0, so it has to be greater than 0, and they cannot equal to 1. You'll also notice some familiarness with the domain and range, but it's backwards of what exponentials are. So our domain is actually 0 to infinity, and our range is negative infinity to infinity. It switches from what it was for exponentials. There's a reason for that. We'll talk about it in a moment, but for right now, we're just going to jot it down. Almost all calculators do not have the ability for you to enter a log in them and have your own chosen base, like where my a is down there. They only have 2 entries for logs, and we'll talk about how we sort of get around that in a future lesson. It won't be today. But there are 2 logs that show up in your calculator. One actually says log. When that shows up, it's actually using a base of 10. We use base 10 because we have 10 digits on our hands, right? 10 fingers and so forth. We have a common base of 10. It's what we use for everything. All of our number system is based on the base 10. If you think about metrics, metric system is based on base 10. It's commonly used. This is called the common log. The other one that you see used is one that doesn't actually read log at all. It reads ln. And that's how I usually say it, is ln. That's not really very accurate. We should say natural log every time we say that. You might think, well, then why did they write it as ln instead of like nl? If you are aware of other languages much at all, Spanish is a good example. Our adjectives and our nouns occur in a different order than they occur in many other languages. So when we might say pretty girl, someone else might say girl pretty in the other order in their language. That's another way of doing that. So when we see log natural, right, we call it natural log. They would say log natural. That would put the L and the N in the opposite order. So that's why that's happening there. So this is understood to be log base 10 of x. This is understood to be log base e of x. And you'll remember we saw e pop up at the very end of section 4.1 when we did our applications inside of a continuously compounded interest formula. Do y'all remember that? It's that same e that's popping up here as well. So the first thing that I want to do in this section is to connect this back to exponentials and show the relationship between the two. And then we'll move on to some other features of these. So the first thing we're really going to do is just learn how to take a log equation and rewrite it as an exponential equation. We're not solving, we're not doing anything else, we're just rewriting. So I encountered another student who was a TA at the time, just like I was at the time, who taught this sort of method or visual demonstration, and I loved it, and I've used it ever since. So what this actually does is I want you to draw a little circle around the 3, the base 3, and I want you to draw a scorpion tail. Okay, if you've never seen a scorpion, you probably haven't lived in Oklahoma long enough. All right, we have scorpions. They will enter my house. I can't remember if it's when it's too dry or too wet. It's probably when it's too dry. And I've had 2 of the children in my house stung by scorpions before. It's no fun. But this is your imagery. It's a scorpion tail. Okay? So What this imagery does is it tells you, as you follow along the arrow, how to rewrite this equation. The 3 that's located and circled down the before, in the base, has the word base attached to it. This is log base 3. Well, it's also then going to be the base of an exponential. So it's 3. And if we follow our arrow around, or our tail around, we encounter the 4 next. It will be the exponent on the base 3. And what we equal is where we land, which is an 81. I'm a super visual person, so I think this is great in terms of being able to get them all in the right place as we rewrite. There's not anything else I'm asked to do in this problem. I'm just rewriting, and that's all I'm doing. I'm done. Now, it's actually a true statement. If you took your calculator, or if you happen to know this particular arithmetic fact, 3 to the power 4 is equal to 81. That is correct. This is only one where we have all the numbers sort of evaluated in there. Part B. Part B says log 1,000. What is the base of this log? 10. Because it is a common log. Okay, again, anytime you see log and you don't see a base, it's an understood base 10. You can kind of think of it like when you see square roots, right? When you see a square root, it is understood that there is a 2 index inside of here. It's understood. So when we see log, we have a common log. It's understood to be a base 10. But we do the same process again. We circle our 10, and we draw our scorpion tail around. The 10, which was the base of the log, is now the base of an exponential. As I move around, the exponent is what I cross to the other side to get, the z. And it lands or ends on the number 1,000. This one, we could solve. We could figure out what z is equal to, but that's not the directions. The directions are just to rewrite. So we're done at this point on the rewriting. Okay, is everybody okay so far? Okay, so this takes logarithms and turns them into exponentials. Next, we're going to take exponentials and turn them back into logarithms. So the process is quite similar. We circle the base and we draw our scorpion tail around. But what you have to recognize as you rewrite is that over here, when we rewrote, the log was no longer present. Over here, where there is no log, it will now come into play. So I now have a log. The circled base 10 in the exponential is now the base of the logarithm. Was the base of an exponential, now it's the base of the logarithm. And if I follow this around, I encounter what's on the other side, the w next, so the w comes next in my equation. Log base 10 of w. And it equals where I land, which is a 5. Yep, Bailey?
Do you have to put the 10 since...
That's what I was going to do next. You're exactly right. So this is sort of the understood expression of what we're doing in terms of the way I circled things and so forth. But if you were to look in the back of the book, or if you were to want to do so, you don't have to write the 10. It really would just be log of w equals 5, because we understand that a base 10 is the same thing as not writing any base at all. So either of those would be correct versions of the answer. Yeah, great observation. Okay. Now, part B has it sort of written on opposite sides. If that bothers you, you can adjust it. But you can circle it and draw your scorpion tail the other way as well. It has to cross the equal sign, no matter where the equal sign is. So this time my scorpion tail went to the left, because that's where the equal sign was to the left. Okay, the circled part is my new base. So again, I'm turning it into a log expression. The base of the exponential is b, so the base of my log is now b. As I'm following it around, across the equal sign, I hit a z. So this is log base b of z. And I land on the exponent, which is a k. Okay, what do you think? It's okay? Okay, so we're going to go one step further now. I mentioned over here on part B, we could solve for z, right? That's something we could do if the directions indicated that we were to do so. So that is what our directions are going to indicate we're to do on the next 4 problems. We are to solve for the variable. Now, you don't see the variable, right? So what we're actually going to do on each one of these is turn these into equations where they are equal to an unknown quantity, in this case, our variable x. Okay? And then we can operate just like we did on the last set of problems where we draw our scorpion tail and we rewrite them. So I circle my 2, I draw my tail around, and I will rewrite. 2 across the equal sign puts me at an x exponent, and it will equal a 16. And we solve problems like this in section 4.1. Our goal was to always get the same base so that we can ignore them, right? Get something to match and then ignore them and look at the exponents. So we're going to be able to rewrite each one of these in that way. The 2 raised to the power x, 2 is prime, there's no factoring possible, but 16 is not. So I can factor 16. How will 16 factor? Yes, it's 4 times 4, or you can break it down further, of course, into the 2's, just like y'all are doing. So you have 4 2's. So my 2 to the x is on the left, my 2 to the 4th is on the right. Bases match, so we ignore them. We don't cancel them, we ignore them, and we set the exponents equal. So what does my value equal? What does x equal? 4, right? So these pieces are now equal. X equals 4 is where I end my problem. Okay, let's do one more. Same way. I set it equal to something. You can use your favorite variable if you wish. It doesn't have to be an x. I circle my base and I draw my tail around. So this is a base now of 1/5 as an exponential base. I cross to the power of x on the right-hand side, and it equals where it lands, which is a 25. Now, neither 25 nor 1/5 are in a form that's very usable. We're going to adjust them both. I'm going to start with the 25 because I think that it's pretty clear it works a lot like the 16. 25 breaks down into what? Yeah. 5 and 5, or 5 squared, right? And 5's prime, I can't do anything else with it. So I'd like to take what's over on the left-hand side, my 1/5, and rewrite it as 5 to some power. What would it be? -1. And there's an x over here on the outside, so some of you are already combining those, which is great. You're right, we want to combine the x and the -1, and that happens, that happens with multiplication. So this is 5 to the -x equals 5 squared. You could probably look at this and tell me now what x has to be, but if you can't immediately, just set your exponents equal to each other and solve. What is x? -2. So let me pause right there to say, right now, from the things that I've taught you, you have no way to use your calculator to verify a and b. You will later. I'll still expect that you do the problem like this, but you'll have a method to use your calculator to verify them later on. Okay? However, on C and D, your calculator can be used to verify them very quickly simply because of the problems that they are. If you want to use your calculator because it's log, plain log with the common base of 10, you can do that on problem C and on problem D because it's natural log. But for the sake of learning and thinking about how we do this, I want to show you why it works too, because it's not a very good answer to say because my calculator said so, right? I mean, it really lacks some sort of authenticity of understanding what's going on. And it's not hard. So we're going to set this equal to x, and we're going to remember, of course, that this is the common base of 10. So we're going to draw our scorpion tail around. 10 is the base of my exponential. The x is the exponent, and it lands on the 10 over here. And that 10, of course, has no exponent, so it's an understood exponent of 1. So I have 10 to the x on the left, and I have 10 to the 1 on the right. What is x? It's 1. And for those of you who've already tried, did your calculator tell you that too? Did you type log 10 and it told you back 1? Absolutely. But here's why. And this is the reason why. We're going to do the same thing with ln1, natural log of 1. Again, it's an understood base e, and it's going to equal to our unknown variable. We're going to circle the e and draw our arrow or our tail around. This is e. Across to the other side, it has an exponent of x is equal to 1. What can you raise any value to and get back 1? 0. So this exponent must be 0. And again, you can confirm that with your calculator. You hit ln, you hit the number 0 or the number 1, and it will end up with the answer of 0. It will confirm for you. But this is the why behind it. Yes, Jonathan.
So there's no value, you just kind of put 1 in there, like where the 10 and the E are?
Well, there's no value because they have an understood value, kind of like my square root. If I have a square root, it's an understood 2 inside of that index. It's also kind of like what happens when there's a number 1 here, right? If there's no number here, we know it's a number 1. So this happens right over here, back here where we talked about it. Anytime you see log with no base listed, it is base 10. And anytime you see ln, it means log base e. They're just used commonly enough that they have another form in which to write them. Is that good?
Yeah.
Okay. All right, we're going to shift gears to graphing. Is there any questions over the rewriting and solving at this point? We're going to come back to some more solving issues at the end of the class. Okay, so let's shift to graphs. I'd like to start by recognizing with you that the setup here looks a lot like the setup when we did exponentials. One of my graphs here says a is greater than 1. The other graph says that a is trapped between 0 and 1, right? And when we had those graphs, they looked like this. So this one was y equals a to the x, where the a value is bigger than 1. And this one was the graph of y equal a to the x when a was between 0 and 1. That was our basic original graphs. Now what I'm going to do, and I'll change colors to do it, is that I'm going to overlay on top of these graphs the other equation as well. That is the log graph of each of those types of bases. On the first one, the log graph looks like this. So this is the graph of y equals log base a of x when a is bigger than 1. And on the other one, it looks like this. So this is the graph of y equals log base a of x when the a is between 0 and 1. Okay, so let me tell you where those are sort of coming from, or make a visual connection at the very least for you. Consider the line y equal x, which I will draw in on both graphs. This green dotted line on each graph, it's easier to see on the first one, I think, but it's still true about the second one, is a line of reflection. If you took the yellow line, or the yellow curve, and you reflected it over that dotted line, you would end up with the white curve. Wouldn't you? It's easier to see on the first graph because they don't overlap each other. But it's still true on the second graph as well, right? If you were to think about the graph of the pieces, if this piece flipped over the line that's green, it would give you this piece, and so forth. Do you remember what the relationship is when they have a reflection across the line y equal x? There's a special relationship that exists. They're called inverses. We saw it happen in chapter 2. It's been a little while. They're called inverses. What we actually see happening when there's a reflection over the line y equal x is that the x value and the y value switch places. So, do you remember back on the first slide that I did, where I told you about the domain and range? And I commented that it was the reverse of what happened for exponentials? That's why, because the functions are inverses. So inverses means the x and y switch. Well, domain is x, range is y. So if you switch the x and y, you switch the domain and the range. Now, taking a look at this, you might also notice that we actually previously had, when we were working with exponentials, this line right here that was a horizontal asymptote, right? Remember we had that? Well, now we have a line that's a vertical asymptote, the other axis. So my vertical asymptote, and it's true for both graphs, my vertical asymptote now is the line x equals 0, or the y-axis. Similarly, previously right here, I had a y-intercept of 0, 1. So if I switch x and y, this becomes an x-intercept of 1, 0. And again, it's true on both types of graphs. Over here, this was 0, 1, and now it's the point 1, 0. So everything's like flip-flopping. We had a question in class last time about what happens when the bases are different, right? So it was an exponential. If it said 5 to the x or it said 8 to the x, what's the difference? In terms of the basic shape of the graph, very little. It still has the same basic features. We talked about the fact that it would be sharper, it would be steeper, those kinds of things. The same's true here for my bases and my exponential. It doesn't matter if I have a base that's 10 or a base that's e. In fact, if you take your calculator and you graph in your calculator, right, like in the y equals menu, log of x and natural log of x, they're going to both look like this first graph because base 10 and base e are both bigger than 1. They're basically going to look like the white curve that I plotted there on that first graph. Not going to be much difference of them. Shape anyway, okay? How steep they are, or how close they are to certain axes, that'll shift a little bit, but the basic features will not. So when we get over here to this example with log base 8 of x, all that matters about the 8 is that it's bigger than 1. That's it. And because it's bigger than 1, it looks like the first graph that I plotted. Okay? So over here, it will have a vertical asymptote in the same place it did before. Shift it. It will have an x-intercept in the same place, 1, 0. And the graph will be an increasing graph, like this. You'll notice we never really plot too much in terms of scale along the y-axis, and part of that is because we aren't paying particular attention to that. We're just worried about the basic overall shape. Now we can answer some basic questions about this though. My vertical asymptote's exactly what it was already on that previous screen. It's x equals 0. What's my domain? Close. It's 0 to infinity, yeah, because 1 would actually prevent me from, it would only give me this part of the graph. So I have to get all the way over here to x equals 0 to get me that bottom part of the graph. So my domain is 0 to infinity. What's my range? Right, negative infinity to infinity. Now, just like we did with exponentials, we can have things shifted left and right and up and down and stretched and reflected. We can do all of those kinds of things. In particular, we're going to look at the same equation, log base 8 of x, with a few changes made. There are 3 of them, in fact. Just a few, yeah. There's a negative at the beginning, there's a minus 2 in the middle, and then there's a plus 3 at the end. I kind of like to start with the plus 3. That's the one I tend to go with. What's the plus 3 at the end do? It moves it up 3. So if you imagine, I'll flip back here, I promise, taking this whole graph and just moving it up 3, what we'll do is it'll do something like this, right? It doesn't change the dotted line. It does change your x-intercept, but the basic overall shape would stay the same. What does the -2, that -2 in the middle, do? Yeah, it moves it right 2. So again, imagine this graph over here. Now when I move this graph right 2, it will move the asymptote as well. It'll go like this, right? So this is what happens when I move it right 2. And I know I'm going to have to move it up 3. Like both of those things are going to happen, right 2 and up 3. But there's one more value affecting this, and that's the negative in the front. So Corbin, tell me what you're seeing happen there. It's reflection. And in the air, you drew me the reflection in the right direction too. This is a reflection over the x-axis. So generally speaking, it takes the graph I have right here and it flips it down like this. So it ends up looking like the other graph over here that we drew once we flip around the x-axis too. Okay, so we are going to have to shift it right. We are going to have to flip it. We are going to have to move it. All those things are going to happen. So we're going to effectively do all that. I'm going to actually do my dotted line with my new asymptote first. So this is my line for my asymptote at x equals 2. And we can write our vertical asymptote down then now as x equal to 2. We know the basic graph shape has to be doing this, right? I mean, that's the shape, generally speaking, we need. But we need what would have been the x-intercept, which has now been shifted. So right now, this would be the number 3, 0, right? But it needs to, not 3, sorry, 2, no, it was 3, 0. I wrote it right, 3, 0. And it needs to go up 3 as well, correct? So that 3, 0 will shift up 3 because of my positive 3 at the very end. So this will be my new point right here. So you should have a point at least plotted when you do this, and it should be that shifted point. The general overall shape also then looks like this. What is my domain?
2 to
Good, 2 to infinity, because the dotted line starts where I can start values just right after it, right? How about my range? You got it, negative infinity to infinity. Any questions on graphs? Okay, last thing we're going to look at today is solving equations. I've specifically chosen 4 that look kind of different. In each of the problems, what you'll see, we'll just look at them all briefly first, is you'll see the x that I'm trying to solve for trapped somewhere. So in the first one, the x is trapped inside of a log. The second one, the x is trapped inside of an exponent. The third one, the x is trapped inside of the base of a log. And then the last one, again, the x's are trapped inside of the log expressions themselves. So we're going to be doing a lot of shifting between logs and exponentials, both directions, to try to untrap x. Because somehow I have to have at the end of the problem x equals. And the way that we do that is by getting our exponents out of those locations, or not our x's out of those locations. So on the first one, just like we were doing earlier on, we're going to do our scorpion tail. We're going to circle the 4 and draw our tail around. We have a 4. I draw an X. We have a 4. It crosses to the other side of the equation where it's a 1/3, so it's a power 1/3. And it equals where I land, which is an X. Now, the reality is that it's solved for X now. But that's not a very familiar looking type of number to us. We don't typically go around writing 4 to the 1/3. That's just not something we use typically. A more natural way for us to write that and to remember is that the 1/3 power is the same thing as a cube root. So generally speaking, let me just remind you up here that we talked about this before, but if you have an m over n exponent, the n part becomes the index of a root. The m part, which we'll see happen in a moment, still is the exponent on the variable x. Okay? But then we're done. We can't do anything else that would keep it exact. It's just going to be this irrational number, cube root of 4. If it said cube root of 8, we would do it. We would simplify, because that's something we can take a cube root of and get, an actual exact answer, but we can't do that with cube root of 4. All right, B. The x is trapped in the exponent. And I should make note that I can't change the 12 to be 5 to a power. Right? That's how we've approached this before. We need the same base on both sides. Okay, great, but 12 doesn't do that. It just doesn't. So we're out of options from the things we've done earlier in terms of getting the same base on the same side, so we're going to do a scorpion tail. I do recognize that puts us back into a log form, but that's okay. It will now be a log. The base of the log is 5. Crossing to the other side puts me at 12, so that's what's next to the log base 5 of 12. And it equals my exponent 3 minus x. That's actually really good. The x is no longer trapped in an exponent. I just need to move this stuff that's next to it, right? I can solve it for x now. So in particular, I need to subtract a 3. While you are okay if you choose to write minus 3 after the 12, I would encourage you not to write it that way. That 3 and that 12 cannot combine. That 12 is trapped inside of a log. It's being operated on. It's like if you had it underneath a radical. I can't just pull something else underneath a radical. I can't just pull something else inside of a log. It doesn't work like that. So I think what makes it a little bit easier to remember that they're separate is to write the negative 3 in front. And then I have plus log base 5 of 12. There's a negative in front of the x, so I just need to divide both sides by negative 1. That gives me x equals on the right, and it changes my signs on the left. So the negative 3 becomes a positive 3. The positive log becomes a negative log, base 5 of 12. And as much as it will pain you to do so, you can go no further. Now, we will have a point where we can go further for an approximation. That will happen eventually. But there's no way to get this any more accurate than it already is, even though it looks kind of funky. I don't know. So we stop right here, and our answer is what it is. Kind of like that cube root of 4. Can't simplify it without losing accuracy, so I leave it as is. Okay. Let's try another one. Trapped as a base. Okay. So we're going to take our x, and we're going to draw our scorpion tail around. This is x. On the other side makes my power a 4/3. And it equals where I land, which is 1/16. Now I wrote this over here. I'm going to copy and paste it since we need it on our other screen. I have x to the 4/3. That's the same form as x to the m over n. So this rewrites as the cube root of x to the 4th. You can put the 4th underneath with the x. You can put the 4th on the outside. It doesn't make any difference. It's the same thing either way. Now there's two things that we need to do to solve this for x. We need to get rid of the cube root, and we need to get rid of the power 4. Does everybody agree on that? Okay. So the way we get rid of a cube root is we do its inverse, which is we cube. The way we get rid of a power 4 is we do a 4th root, which is the inverse of a power 4. So we're going to do both things, and while we technically can do them in either order, there is a nice way to do this one, and it is to do it to the 4th power first, and here's why. We saw earlier that 16 broke down into 4 times 4, and the 4s broke down into some 2s. Do you remember that? This is the same as 1 over 2 to the 4th. I have something raised to the power 4 on the right-hand side, and I have something raised to the power 4 on the left-hand side. So it is advantageous to go ahead and take the 4th root on both sides because I have things with powers of 4 on both sides. This 4th root and this power of 4 cancel. This 4th root and this power of 4 cancel. If I cube it first, that's 16. It will then be 16 cubed. And breaking that down into powers is harder than breaking 16 down, not into powers, into factors, is harder than breaking 16 down into factors. So on the left now, I'm left with the cube root of x because the power 4 and the 4th root canceled. And on the right, I'm left with 1/2 because the power 4 and the 4th root canceled. You might say, well, don't I need to do the 4th root of 1 on top? Yes, you do, but the 4th root of 1 is just 1, so that's, not a problem. And then my last step is to eliminate the cube root by cubing. That gives me x on the left. 1 cubed is 1, and 2 cubed is 8. You got it. So my value ends up being 1/8. All right, the last problem is going to be your favorite one of the day, and I'm not being facetious. I mean it for reals. You're going to like it. Okay, so do you remember back in section 4.1, our goal was always to get the same bases on the sides and then to ignore them? Remember that? Okay. Well, if I have the case, like I do here, where I have the logs on both sides with stuff inside of them, I can also ignore the logs. They don't cancel, but they can be ignored, which means what I really need is I need my interiors to equal. The 2x must equal 24 minus x squared. The caveat to that, of course, is that now you have a quadratic that you have to solve like we did back in chapter 3. But all of your exponentials, logs, changing things with scorpion tails and so forth, none of that applies because the log base 3 matched on each side. So I'm going to move the 24 and the negative x squared over with my 2x. So I'll have an x squared, I have my 2x, and then I have a negative 24. We will attempt, and we will be successful here, with factoring this. Negative 24 at the end means the signs need to be different. I need a positive 2 in the middle, so I need a positive 6 and a negative 4. Okay, so far so good. I will set each one of these equal to 0. Okay, so x is 4 and x is negative 6. While I would love for it to be true that you can stop right there, you do have to check one thing. You have to check to make sure that when you ignored the logs, you didn't inadvertently introduce any extraneous solutions. What does that mean? Do you remember earlier on, what was our domain for logs? 0 to infinity. I can't have a negative inside of a log. And if you try in your calculator, it will tell you domain error. If you put in log of negative 12, which is what will happen here in a minute, it's going to say domain error. So we have to check each of these and make sure that we don't, in fact, get a negative inside by putting them inside of here to check. So if I put in the number 4, obviously 2 times 4 is 8 is fine. Over here, 8 squared is 16. 24 minus 16 is fine. So this one right here is an actual real solution. It works. Now, it's worth noting that you could get 2 solutions and neither one of them work. The other one, negative 6, does not. Because when you attempt to put the negative 6 in here, you get 2 times negative 6, which is negative 12. Can't have the log of negative 12. It's extraneous. So this is an extraneous solution. And the reason, just as a reminder, you don't have to write this down like in your own homework, is because the log base 3 of negative 12 does not exist. It's undefined. All right, so this section, 4.2, due next time, and we will continue in our discussions of Chapter 4 after that. Have a great weekend.